In this lesson, we're going to investigate some derivatives of trigonometric functions, beginning with the rules for differentiating sine and cosine, and then we'll move on to the other trig functions in a bit. What's nice about sine and cosine is they are effectively their own derivatives. So the derivative of sine is cosine, and the derivative of cosine is almost sine, but it's the negative of the sine function. So you want to be careful with that. Make sure you get the negative in the right place. One thing that you can count on is throughout all of differentiation, all of the co-functions have negative derivatives. So cosine has a negative derivative, cosecant has a negative derivative, and cotangent has a negative derivative as well. So that makes it easy. Let's take a look at the proof of this derivative for sine x. In order to do the derivative with respect to x of the sine function, we will need to switch off to the limit definition in order to show that this works the way we expect it to. So that is the limit as delta x goes to 0 of the function itself evaluated at sine of x plus delta x. So, sorry, the function evaluated at x plus delta x. So that gives me the sine of x plus delta x minus the function itself, so minus sine x, all over delta x. So that's just using my difference quotient with the limit definition of a derivative. Now, there is a rule from trigonometry about how you can handle the sum of the sine of an angle. So if you have the sine of some two angles that are added together, there's a formula that tells you how you can split that up. We need to use that. So this is going to be the limit as delta x goes to 0. The sine of x plus delta x will be the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second, and then minus sine x and all over delta x. Now that we have that split up, there's some similarities here. So one thing that I notice is in my first term, the sine x cosine delta x, and the last term, negative sine x. There's a common factor of sine x, and I'm going to group those together and factor that out. So this would be the limit as delta x goes to 0 of sine x times, if I pull that out of the first factor, I'm left with cosine delta x. And if I pull sine x out of the second factor, which is negative sine x, then that leaves me just a minus 1. And then I still have the middle term, so plus cosine x sine delta x, and this is all over delta x. Okay, now the next thing that I can do is split this up a bit. Whenever you have the limit of two things added together, you can split it up into two separate limits. So I'm going to take advantage of that. But also, if you have parts of your function that are multiplied and aren't actually changing with respect to the variable delta x, for instance, I have a sine x and a cosine x in these terms, I can factor those out because they're effectively constants with respect to the variable delta x. So I could write this as sine x times the limit as delta x goes to 0 of cosine delta x minus 1 all over delta x plus the cosine of x times the limit as delta x goes to 0 of sine delta x over delta x. And the important thing here, these remaining limits are actually limits that we've seen previously in the course. We evaluated them, so all I'm going to do at this point is just use that evaluation to come up with my answer. You could go through a table and prove these if you aren't certain as to how these actually work out. Initially, plugging in your delta x as 0, you get 0 over 0 for each one. But you can prove that this limit, the first one for instance, that thing goes to 0. And the limit over here, this goes to 1. So effectively, I have the sine of x times 0 plus the cosine of x times 1. Anything times 0 is just 0, so that thing becomes 0. And then cosine of x is just itself. So that gives me the cosine of x. So the derivative of sine is cosine. The derivative for cosine is fairly similar. We'll walk through it real quick here. And to do the derivative of cosine, just like before, we start with our limit definition. So the derivative with respect to x of the function cosine x is going to be the limit as delta x goes to 0 of cosine x plus delta x minus the cosine of x all over delta x. And here we use, again, the same sort of formula from trigonometry, except for the sum of angles for cosine. But the formula is a little bit different here. It looks like this. So limit as delta x goes to 0. The cosine of the sum of angles, it's the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. But we're sort of in the same situation here where we can factor out a common factor of cosine x from the first term and the last term. So let's begin doing that. So limit delta x goes to 0. I would have cosine x times cosine delta x minus 1, and I'll go ahead and split these up, divided by delta x, then minus the limit as delta x goes to 0 of the sine x times sine delta x all over delta x. And what happens here is the same sort of thing. When I take the derivative, or sorry, the limit as cosine delta x minus 1 over delta x, that limit of this piece right here is going to go to 0. And because that's going to go to 0, cosine x times 0 disappears. So all of that goes to 0. The limit of sine delta x over delta x, that goes to 1. So then I have negative sine x times 1, which results in negative sine x. Okay, now let's see these used in some examples. So starting with the function f of x equals 3x plus sine x, let's find the first derivative of this function. So the first derivative, if we have terms that are added, we can take the derivative term by term. So 3x, it's a linear function. Its derivative is going to be the constant function 3. The derivative of sine is cosine, So this derivative is simply 3 plus cosine x. Things can get a little bit more complex if you happen to have a product rule involved. So we have the product of functions. I'm going to use 5x squared as my first function, cosine x as my second function. So when I use the product rule to find this derivative, I'll do the first times the derivative of the second. So the derivative of cosine is negative sine x, plus the derivative of the first, which would be 10x, times the second. Then simplify as you can, combine coefficients and that sort of thing. There's generally not a lot requested here. Negative 5x squared sine x plus 10x cosine x. And there's a final answer. Next, we'll do an example that requires the quotient rule. So q of x equals 3 sine x over x squared plus 2. So when I do the quotient rule, I kind of come off to the side, write my numerator and denominator side by side, take the derivative of each. So this would be 3 cosine x, and this would be 2x. And just remember, these two corners multiply first. So the derivative of the function q is going to be 3 cosine x times the quantity x squared plus 2 minus, I'll go ahead and do some combining here, so 2x times 3 sine x would be 6x sine x, all over the original denominator squared. And here you could probably do a little bit of simplification. Looks like the 3 and the 6 have a common factor you could pull out. That's probably about it. This is probably about as simple as you're going to get. So this is an acceptable final answer here. Now let's move on to the derivatives of tangent and cotangent. And it would be great if the derivatives of tangent and cotangent were simply negatives of each other, as in the case with sine and cosine. That's just not how it works, unfortunately. The rules for derivatives of tangent and cotangent are: the derivative of tangent of x is secant squared x, and the derivative of cotangent of x is negative cosecant squared x. Now, cosecant and secant are kind of like partner functions here. They're co-functions of one another. So there's similarities in how these formulas work, which is nice because that makes it easier to remember. But also notice cotangent, being the derivative of a co-function, as I mentioned earlier, has the negative derivative. So the derivative of any of your co-functions is the negative one. Now, to see where these rules come from, it really is instructive to use a proof to find out. Because it might seem like they're coming out of left field at this point, but once you see the proof, it makes sense. So if I am doing the derivative with respect to x of the function tangent of x. Now, I'm not going to go to the limit definition here. I'm sure there's a way of using the limit definition to come up with this result, but there's actually an easier way based off of rules we've already established. So for instance, one thing that we know from trigonometry is the definition of the tangent function. The tangent function is sine divided by cosine. So the sine of x divided by the cosine of x. Now, given that, and our knowledge of what the derivatives of sine and cosine are, which we've already proven, we can use the quotient rule, because I have two functions divided. In the numerator, it's sine x, In the denominator, it's cosine x. Derivative of sine is cosine. Derivative of cosine is negative sine. These two functions multiply together first. So what I end up with here, using the quotient rule, is cosine squared of x minus the negative sine squared of x, which means plus sine squared x. Oops. Now, this gets divided by the original denominator squared. The original denominator in this was cosine of x. So it's divided by cosine squared x. You've probably already recognized the numerator is the form of the Pythagorean identity. So cosine squared x plus sine squared x is equal to 1. So this becomes 1 over cosine squared x. And 1 divided by cosine squared, that is the definition of secant squared, which is where we get the rule for this derivative. I'm not going to do the proof of cotangent. It's nearly identical and doesn't really give us much more insight. So, moving on. Let's do an example, but let's find the equation of the tangent line to y equals 2 tangent x at x equals pi over 4. Okay, to find the equation of a tangent line, we need to have a point that exists on the graph of interest, and we need to know what the slope of the tangent line is at that particular point of interest. So the point on the graph, let's start there. The point on any graph has the coordinates x comma y, and y is defined by a function, so effectively it's x comma 2 tangent x. So let's evaluate 2 tangent x. So my y value is 2 tangent pi over 4, and tangent pi over 4, if that's one that you're not familiar with, develop your unit circle, whatever you need to do to come up with your answer here. But this one is just 1. So this would be y equals 2 times 1, or 2. So the point on the graph is pi over 4, 2. All right, so that's half of the things that we need for a line. So we need a point on the line, but we also need the slope of the line. The slope of a tangent line comes from the derivative. So the slope of the tangent is going to be the derivative evaluated at pi over 4. So let's begin getting the derivative function. So y prime, so 2 tan x. The derivative of tangent we just learned was secant squared. So this is going to be 2 secant squared x. Now the slope of our tangent line is that derivative evaluated at pi over 4. So this is going to be 2 times the secant squared of pi over 4. And this may be something that you look at and you say, oh no, I don't remember enough trigonometry to evaluate this. I'm just going to quit. Well, don't do that, because I guarantee you probably have enough knowledge of trigonometry to figure this out, even without drawing a unit circle. And here's why I believe that. So number one, you never actually have to evaluate tangent, cotangent, secant, or cosecant. You can always switch things back into sines and cosines. So this, first off, is effectively 2 times the value of secant at pi over 4 squared. So that's what that secant squared means. Next, we can write secant as 1 over cosine. So as long as you know what cosine pi over 4 is, or are able to figure that out, then you've got it. You don't have to work much harder at this. So cosine of pi over 4, that's the square root of 2 over 2. So this is going to be 1 over the square root of 2 divided by 2. Then that's all going to get squared. Or 2 times the inverse of root 2 over 2 would be 2 divided by the square root of 2. If you square that fraction, this could be 2 times 4 over 2. The 2's cancel, leaving me with a slope of 4. So I now have the slope of this tangent line at 4. So to get the equation of the tangent line, what I have to do is use the point slope form of a line. So y minus y1 equals m times x minus x1, and plug in my point and my slope that I've just found. So the point that we had was pi over 4, 2. So this would be y minus 2 equals 4 times x minus pi over 4. Or y minus 2 equals 4x minus pi, or y equals 4x minus pi plus 2, which looks a little bit strange simply because negative pi plus 2 isn't something that we can combine without switching to a decimal answer. But this is perfectly fine. This will give us the equation of that tangent line. Now we're on to the derivatives of secant and cosecant. And similarly to tangent and cotangent, these aren't just simply derivatives of each other, but the rules are this. The derivative of secant x is the secant of x times the tangent of x, and the derivative of cosecant of x is the negative cosecant function times the cotangent function. Let's take a look at the proof of secant of x, and that will help you understand why it is the way it is. So if I am taking the derivative of secant x, then what I know from trigonometry is secant of x is defined as 1 over cosine. And because I know how the derivatives of cosine work, and I have the quotient rule, I can develop this derivative in the same manner that we did the last one. So using the quotient rule, the numerator is 1, the denominator is cosine x, so the derivative of 1 is 0, the derivative of cosine x is negative sine x. We multiply these two together first in the quotient rule. So this would be 0 times the cosine of x, which is just 0, minus negative sine x times 1, which becomes plus sine x, all over the original denominator squared, which would be cosine squared x. So effectively just sine x divided by cosine squared x. Now there isn't any particular rule of simplifying something like this directly. However, one thing we can do is split some things up. So I could write cosine squared x as cosine x times the cosine of x, and make this sine x over cosine x times 1 over cosine x. Because the numerator still multiplies to sine of x, the denominators multiply to cosine squared. Sine x over cosine x is the definition of tangent of x. 1 over cosine x is the definition of secant of x. So there we've established the derivative of secant is the secant of x times the tangent of x. And let's take a look at a derivative here. Let's find the derivative of f of x equals 2 secant x minus x times the cotangent of x. So the derivative here, I can split things up about that minus. All right, anytime I have individual terms that are added or subtracted, I can split and do the derivative of those pieces separately. So I can make this the derivative with respect to x of 2 secant x minus the derivative with respect to x of x times the cotangent of x. Writing it in this way is basically saying, I know I need to do my derivative, but I'll do it in a second. I'm just trying to take my time with steps and not make a mistake. Now, the derivative of 2 secant x, that's pretty straightforward. We just use the rule we established a second ago. So the derivative of secant of x is secant of x times the tangent of x. So that first term becomes 2 secant x tangent x. The next part, however, this is a product of functions. So I need to make sure I use my product rule when I come up with this derivative. So I'm going to subtract in parentheses. So I'm going to take the derivative of the first times the second minus the first times the derivative of the second. The derivative of a cofunction is negative, and the derivative of cotangent is negative cosecant squared in particular. Okay. Should clean things up here, and shouldn't take much effort to do. So 2 secant x tangent x minus the cotangent of x. And, well, actually, I was going to write that as a plus because I have a negative on the outside of these parentheses that would distribute, but there's also another negative on the inside, so I have 3 negatives here, which an odd number of negatives results in a minus. So it's going to be minus x cosecant squared x. And that's my final answer.